Well, so this is something I already mentioned, so that the fact that when we know for sure that the vector field is conservative, it doesn't matter what way you choose to go from point A to B. It could be along like this x equals y squared, or along y equals x cubed, or some other crazy way, even if it takes forever. Well, the vector field is going to take the same work of 1/2 in this case as a result whenever we know that the vector field is conservative. Okay, so here um, let's just formalize that thing we mentioned before. So if f is continuous on an open and connect in a non-open connected region, then the line integral of f dr over c is independent of the path if and only if f is conservative. All right. Now, well, what about this kind of regions? What do we mean by by simply connected, we can go about this is like the generic picture of a simply connected region, to go from point A to point B. There are situations in which we cannot use this theorem when, yes, even when in this case, well, the regions are not connected. That is, A is in one set, is in one region, and B is in a different region. Well, we're going to look at something later for this kind of situation. So, really, I mean, uh, again, this is just to say that whenever really to repeat ourselves, that whenever we have a conservative vector field, that integral is independent of the path, and all we do is use the fundamental theorem of line integrals, and that's it. So let's go over another example and check the difference of the problem. So consider the force field f of x, y, z equals to y ln of z in the direction of I plus x ln of z in the direction of j plus x y over z in the direction of k. So number one, show that the line integral is independent of the path, and calculate the work done by f on an object moving along the curve C from 1, 1, 2 to 3, 4, 8. Well, so here we're putting things together. So the fact about the independence of the path, and notice in this case they're not giving us a function to work on. I mean, they're not giving us some parametric function whose initial point and final point. No, they're just giving us the 2 points. And there's infinitely many ways to go from 1, 1, 2 to 3, 4, 8. We can go as in a straight line, in a curve, or some other crazy way. And in that case, it doesn't matter the path that you choose to go from point A to point B if the vector field is conservative. So let's see what about it. So number one, let's list F, G, and H. F, which is y ln of z, g, which is x ln of z, and h equals to x y over z. So we need to make a test again. We need to test whether this vector field is conservative, and if so, find a potential function and use the fundamental theorem of integral lines. All right. Or line integrals rather. So that's part A. So part A, we need to show that the partial with respect to y equals to the partial with respect g. Well, the partial of f with respect to y equals the partial of g with respect to x. So the partial of f with respect to y, so that's the derivative of y, which is 1, that's just ln of z. And the partial of g with respect to x, that's also, the derivative is only 1 times ln z, which is ln of z. So far so good for the first condition. Letter B, let's show that the partial of f with respect to z equals to the partial of h with respect x. All right, so the derivative of f with respect to z, that's actually to differentiate ln of z, which is 1 over z times y, so that's y over z, and the derivative of h with respect x And that's, oh, wait a minute. Do I have something? Let me double check. Oh no, that's fine. With respect to x, that's just 1 times y over c, which is y over z. And for letter C, we need to show that the partial of g with respect z equals the partial of h with respect y. Okay, so the derivative of g with respect to z, that's again ln of z, the derivative is 1 over z times x, so that's x over z equals h with respect to y, so that's also x over z. So the three conditions are satisfied here. That means the vector field is conservative, and therefore there exists some function phi of xy whose gradient is the potential function. The gradient is actually this vector field. All right, so let's go ahead and find that potential function. So number one, by partial integration, phi of x, y, z equals the integral of f with respect to x, which in this case, the integral of y ln z with respect to x, that's simply xy ln z plus some constant c that depends on y and z. Doing the second partial integration, that's the integral of g with respect to y. Well, so that's the integral of x ln z dy, and that's simply xy ln of z plus c of x and z. All right. And the third partial integration, that's for phi of x, y, z equals to the integral of h with respect to z. And need to be careful here. So that's going to be the integral of xy over z dz. So xy are constants, so we are really integrating 1 over z. And what's the integral of 1 over z? ln of z. So that's going to be xy ln of z plus c of xy. All right. And while putting everything together, x, y, ln z, x, y, ln z, x, y, ln z, we don't have anything else. All right, so therefore, v of x, y, z, that's actually x, y, ln z. That means this is our potential function. And that's the one that we're going to use to evaluate the line integral from the point 1, 1, 2 to 3, 4, 8. So the integral, the line integral c of f dr, that's going to be, using the fundamental theorem of calculus, phi of 3, 4, 8 minus phi of 1, 1, 2. In other words, x, y, ln of z evaluated from 1, 1, 2 to 3, 4, 8. All right? And as usual, upper limit minus lower limit, but this time we're doing this using 3 variables and order triples. So this will be x, y, ln z, so that's 3 times 4 times ln of 8 minus 1 times 1 ln of 2. And in this case, well, 3 times 4, which is 12. 12 ln of 8 minus, what's this? Minus just ln of 2. And if you got something like this on the exam, this is fine. However, if you want to simplify this a bit further, we can use laws of logarithms, properties of logarithms to combine this together. However, in this case, you might want to write this number 8 as 2 to the third power. So that's 12 ln of 2 to the third power minus ln of 2, and then use that the smackdown bracket will rule for logarithms. So this 3 jumps in the front. So that's 3 times 12 ln of 2 minus ln of 2. And 3 times 12, which is 36. ln of 2 minus ln of 2. So 36 ln of 2 minus 1 ln of 2. This is 35 ln of 2. Well, in this case, well, I don't know what about my MATLAB, if my MATLAB would accept this as an okay answer. You know, the usual, although your answer is correct, it's not simplified to lowest term, blah, blah, blah. Just in case, well, properties of logarithms, all right? So, I mean, that's another example. And, oh no, there's one last part, yes, like putting everything together about line integrals over closed curves. Well, what is a closed curve? So a curve is closed, is considered closed whenever R of A is exactly the same as R of B. By the fundamental theorem of line integrals, we can conclude that if f is continuous and conservative over the region, then the line integral over every closed curve is going to be 0. What about it? I mean, let me give you an example of a closed curve. So, I guess the easiest example is the circle, isn't it? Where we start at, the circle from 0 to 2 pi. All right, this is A, this is B. So the function, the circle evaluated at 0 is going to be 1. You know, the radius equals 1. And this is a closed region. Go back to the same point. R of A is equal to R of B, for example. Cosine of 0, which is 1. Cosine of 2 pi is also 1. So R of A equals R of B. All right? And, well, so these integrals are going to look a little different. Well, actually, their notation. So to distinguish these line integrals over closed curves from the line integrals over open curves, we use the following notation. So this same integral, however, we add a little circle like right in the middle of the integration, and that's to denote that we are integrating over a closed curve, over a cyclic curve. It doesn't have to necessarily be a circle. It could be something else. And, well, so what happens when our vector field is conservative? Well, if the vector field is conservative, well, then the integral is independent of the path, and in this situation, the integral going around the whole cyclic process is just going to add up to 0. Here is a picture of what do we mean by that. So, for example, we want to go from point A to point B. We're going to go via C1. Well, whatever that value is, and again, the path it is not important. We can go in a straight line or in a semicircular way. Either way, we can go from point A to B. However, if we go back in the opposite direction, the value of the integral will be the exact same value, but with the opposite sign because of the opposite direction. For example, if the integral from over C1 is 5, the integral over C2 should be -5. And, well, they are going to add up to 0. So that's one very powerful, theorem or idea about these cyclic integrals or integrals over closed regions. And everything gets summarized here. For those of you who are taking linear algebra, so you have like a sequence of theorems or statements rather, that whenever you have a linearly independent set of vectors, you have a basis, or backwards. If you have a basis, that means those vectors are linearly independent. That is what we call, these are equivalent conditions. So, and here in Calc 3, these three are equivalent. Number 1, f is conservative. That implies that the integral is independent of the path. And if you are integrating over a cyclic, over a closed region, well, then the integral is going to go 0 because you're going to go forward and then back. 5 joules minus 5 joules, overall work, 0, you know? Or you can set this equal to, I mean, if the value of the integral over a closed region is 0, that means that occurs because f is conservative. And at the same time, that occurs because the integral is independent of the path. And of course, that's the same implication on these three. All right, how about we do one example of this to see this in action. So for the force field given by f of x, y, z equals to sine y plus x cosine y plus cosine z j minus y sine z k, show that the integral is independent of the path. So for example, if you see this on a quiz, on an exam rather, what would you do to check that the integral is independent of the path?
The theorem of the line integral?
Of the line. So, well, we would be able to use that theorem provided that the vector field f is conservative, right? So conservative implies independence of the path, and well, in that case, we can use the fundamental theorem of line integrals. And thank you, we don't have to parameterize anything, but otherwise, one of the conditions for conservative vector fields fails. Well, there's no way around. Brute force, parameterizing, the long way, all right? So let's see what about this one? Okay, so that's a check for independence and use the fundamental theorem if it is independent, and to calculate the work done by f on moving an object along the point from the origin to 1 pi halves pi. All right. So as usual, let's list f, y, f, g, and h rather. So f, which in this case is sine y, g, which is x cosine y plus cosine, and h, which is y negative, careful with the sign, negative y sine z. And again, we have to test three conditions, not just one condition. We test only one condition whenever we're working on R2, when in this case we're working in R3. So three conditions have to be tested in this case. So, is the partial of f with respect to y the same as the partial of g with respect to x? Let's find out. Well, partial of y with respect of f with respect to y, that's the derivative of sine, which is cosine. That's cosine y, equals the partial of g with respect to x. Well, that's x cosine y, the derivative of x, which is 1 times cosine, which is its constant multiple. And well, cosine z is constant because we're differentiating with respect x. Well, that's just going to leave us with cosine y, and indeed, the first condition is satisfied. Second condition, h partial of h with respect to z, is that equal to the partial of g with respect to x? Let's find out. So the derivative of sine z, isn't that a cosine z times negative y? That's a negative y cosine z. While the partial of g with respect to x, is that with respect to x again? No, I think no, that should have been h with respect to x. All right, h, not g. We already did that one. Yes, I was looking on my notes, I look at the wrong spot. So hx. So yes, well, hold on. So that, oh yeah, f of z, yes. Again, I need to scroll up a little bit. Yes, thank you. Well, what's this? F with respect to z, there's nothing on z, so that's 0. And h with respect to x, there's no excess of 0. So condition satisfied. And lastly, okay, g with respect to z, is that equal to h with respect to y? Let's find out. So the partial of g with respect to z in this case is simply negative sine z, because everything else does not depend on z, so they get zeroed out upon differentiation. And the partial of h with respect to y will be Okay, negative, or differentiate negative y, that's a negative 1 times sine, that's a negative sine z. Three conditions are satisfied. That means f is conservative. And by the three equivalent statements, that means that the integral is independent of the path. And if we were to evaluate the integral over a closed region to go from point A to point B and then back to point A, the integral will be 0. So yes. All right. So let's find that potential function here. Whew. So phi of x, y, z equals, number one, the partial integral of f with respect to x, which in this case is the integral of sine y with respect to x, which is simply x sine y plus some constant that depends on y and z. The second part for the potential function is the partial integration. That is the integral of g with respect to y, and that's the integral of x cosine y plus cosine z. This one is going to require more terms, but it's all right. Well, x is constant in the first term. In this case, dy. We're integrating with respect to y. And what happened here? So the integral of cosine, isn't that a sine? So that's x sine y plus the integral of cosine with respect to y, that's x, or rather y, cosine of z, plus some constant that potentially depends on x and z. And for the third partial integration, that's the integral of h dz, that's the integral of negative y sine z with respect to z. And careful, because we already have a negative on the integrand along with the sine, because, well, the integral of sine is negative cosine, but that times that negative, doesn't that turn into a positive? So careful there. So that's y cosine z plus some constant that depends on x and y. All right, and so I believe we have a potential function. Let's reconcile everything. So therefore, x, y, z, and that's okay. X sine y. We have another x sine y here. So let's write it down. So x sine y. And what else do we have? No, that's it. Then we also have a y cosine of z, and which is also in the third integral, right? So plus y cosine of z. Do we have anything else? I think that's it, right? That's about it. So that's our potential function. Well, I'm boxing the MyMathLab part, but again, I'm adding this phantom constant of integration that, I mean, technically should be there. Okay, so now that we have a potential function, let's use the fundamental theorem of line integrals to compute the line integral c of f, the integral of f dr over c. That's phi of the upper point, or the final point, minus phi of 0, 0, 0. In other words, we want to evaluate rather x sine y plus y cosine z from the point 0, 0, 0 to the point 1 pi over 2 pi. All right? Upper limit minus, or upper point minus lower point. I mean, you know the drill. What could go wrong about it? I mean, just careful. Just careful, because we have x, y's, and z's all over the place. And it's really easy to plug in the wrong number in the wrong letter, the wrong variable. So x sine y, so that's x, which is 1, sine of y, which is sine of pi over 2, plus y, which is pi over 2, cosine of z, which in this case is pi, and that's the upper limit. And the lower limit, well, everything going to 0, minus, okay, 0 sine 0 minus 0 cosine 0. And although everything gets zeroed out, I mean, just for practice, so just so you can see how do we plug this in. Anyway, I mean, everything gets zeroed out here. And is there anything that, no, not everything gets zeroed out, because sine of pi over 2, isn't that 1 times 1? That's 1. Cosine pi, that's negative 1 times pi over 2, that's negative pi over 2. And that's the value of the integral in this case. So that's the amount of work the vector field would do into moving a particle from the point 0, 0, 0 to the point 1 pi over 2 pi, regardless of the path, because our vector field is conservative. That implies independence of the path. And one last question for this section. And a path begins at 0, 0, 0, passes through 1 pi over 2 pi, and then returns to the origin 0, 0, 0. What's the value of the integral there? 0, right? So that's the integral, the circular integral over c of f dr. That's simply 0 by the third statement, the third implication in this case.